goal of building an ODE that represents the population dynamics, we now want to look at more complex models that construct more complicated behaviors. We start with the critical threshold model. The idea is that if the population is too small, it dies out. We're not interested in looking at big populations. We're just looking at situations in which a population is very small. And the concept is if we have just 2 or 3 rabbits, things are not going to be going well. If we have many of them, we expect them to keep growing. But if we have too few, the population is going to die. So what we want is the right-hand side of our ODE to be negative for some values of the population. So for y between 0 and t, for some value of t, we have that f of y should be negative. So the most easy way is just having a negative parabola. So we build it in the same structure as we just built a positive parabola in the previous video, in which we put f of y equals minus r times 1 minus y over t times y. Now we have the same equilibrium solutions as before, so y equals to 0 and y equals to capital T are 2 equilibrium solutions. But what happens between the two and out of these two is different, because things move away from t, not towards it. So t is an asymptotically unstable equilibrium. For time tending to infinity, everything that started close to t is going away from it. If we solve the equation by hand, we find that the solution is y0 times capital T divided y0 plus t minus y0 times an exponential of the r times t. And we have a problem, because here, depending on the time, we get to a moment in which things can cancel out. So let's look a bit into that. If we start at y0 bigger than t, so on the denominator, the second part is negative, well, there will be a certain value of small t, a certain time, at which the denominator just tends to 0, so the solution tends to infinity. That happens at t star, that we define it, we compute it as 1 over r times logarithm of y0 divided y0 minus t. And when you sort it at y0 bigger than t, for time tending to t star, your solution tends to infinity. The solution tends to infinity in finite time. Obviously, this is not something we want. We expect a population to have always a finite number of individuals, not something tending to infinity after just finitely much time. So we want to combo the logistic growth model that was good for big populations and the critical threshold model that was good for small populations. We do that by just, as simple as that sounds, multiplying the two things together, kind of. So what we have on the right hand side is minus r times the block that we built for the threshold model and the block that we built for the logistic growth model times y. Here we expect the threshold to be smaller than the carrying capacity and r to be positive as well. So what is now the general shape of our right hand side? So f of y, well, this is something that has 3 zeros and swings first negative just after 0, then crosses at value t, then goes up and down again at value k, and for y bigger than k, f of y is negative. So if you're looking at the dynamics of y, you see that for y starting between 0 and capital T, you are pushed towards 0. If you start between capital T and K, you're pushed towards K. And if you start over K, you're also pushed towards K, because y prime there is negative. So if you plot it on a vertical axis with respect to time, you see exactly that. You see 3 equilibrium solutions: y equal to 0, y equals to capital T, and y equals to capital K. And things between capital T and 0 tend towards 0 in an S shape. Things between capital T and capital K tends toward capital K, and things over capital K get down to K. Sorry about that. So here we have a model that does what we would expect a population model to do. If the population is too small, it dies out. But if the population is big enough, then it tends to the carrying capacity. The quantity, the value of population that our environment can sustain.